Hi, everyone. Thanks for joining us today. I'm going to get started quickly because we've got quite a lot of content to get through. So time is of the essence. And in today's session, we're going to be talking about global scale flood modeling. And I kind of debate with myself, actually, whether we should call that automated flood modeling, because really what we're talking about here are large scale automated modeling structures. Today, you are joined by myself, Andrew Smith. I'm one of the founders here at Fathom. I'm a flood scientist by background. I'll be giving you an introduction to the modeling itself and talking through some of the problems that we've had to overcome in building these kinds of models over the past 10 years. I'm joined also by my colleagues, Natalie and Gavin. Natalie will be introducing the problem of integrating flood models with climate models and thinking about forward-looking models. And Gavin, at the end, is going to talk us through the application of these models in the real world. So as I said, I'll begin by talking about Fathom itself, the kind of problems that we're trying to solve, and talk through some of the problems that we have in trying to build these models. And then I'll hand over to Natalie, and at the end, Gavin. We will have time for Q&A at the end, hopefully. So please do drop any questions that you have into the Q&A box, and we will get to them at the end. And our aim today, in terms of the knowledge we're trying to provide you with, is to get an understanding of why these models are important and why we need them and why they're different to small scale models. To also talk about the problems in building them. So hopefully we'll be able to convince you that we do need these tools. Well, then how do we build them? I'll spend some time talking through some of those major problems. And then also you should be able to get an understanding as to why understanding flood risk under future climate scenarios is frankly really, really difficult to do, and in many ways stands alone from other extreme perils. Lastly, hopefully you'll also be able to get an understanding of how you can use these data today in various ways. Firstly, for anyone who's not familiar with who Fathom are, we're formed by a team of scientists at the University of Bristol. Anybody building grid-based two-dimensional flood models can trace the heritage of those models back to that research group. And our aim as an organization is to actually try and provide information anywhere in the world. We've been building models of the whole planet now for a number of years. And it's important to say here that research is a really important part of what we do as an organization. We operate in some ways like a mini research group and publish lots of leading peer-reviewed literature around the kinds of models that we build, and also discussing the implications of those models and what they tell us about risk now and in the future. We don't have much time today, so I'll be touching on some topics and talking through some of the modeling techniques. But as I said, we do try and publish everything that we do. And if you use the QR code on the slide right now, that would take you to our research timeline. And you can, on that research timeline, dig into the details, frankly, as much as you'd like. So hopefully there'll be enough detail there to satisfy even the most interested of modelers out there. Okay, so before we dive into the technology itself, I'll just spend a few minutes talking about why these automated models are required. And if we start really with, I guess, a very high level look at this issue, well, I've just picked a few events that have occurred around the world in the past couple of years. And I think it's becoming pretty evident now, and actually even prevalent in public consciousness, that flooding is indeed a really serious problem that we need to contend with and provide solutions for. It actually impacts, estimates are, around a third of the world's population. So it's the most prevalent natural disaster by some distance. And again, even just anecdotally, you kind of, in the public consciousness, you feel like these events are becoming more frequent and more severe. And it's not just anecdotal evidence. If we look at things like insured losses, and these numbers come from Swiss Re, the large Swiss reinsurance company. If we look at losses incurred from flooding alone over the past few decades, what we can see is that there's been a big amplification in insured losses. Kind of amazingly, the losses incurred in the previous decade of 2011 to 2020 almost doubled those that occurred in the decade before that. And I think that the graphic on this slide that really kind of makes my eyebrows go very high is that in a single year in 2021, you had almost half of the losses that occurred in the entire decade of 2001 to 2010 occurring in a single year. And unfortunately, it will get worse, even if hazard remained the same. And by hazard remaining the same, I mean if the climate was stationary and we didn't have good reason to think that extreme events will become more severe, then exposure to this peril will get a lot worse regardless because of changing urbanization patterns. Research shows us that just down to changing population patterns, we expect losses in the US, for example, to almost double by the end of the century, just down to population growth alone. And I'll go into some more detail around that at the end. And that is actually a pattern that we see around the world, I should add. We see that with increasing urbanization, frankly, all the best places to live are already occupied. So you see that it's the fringe areas that are not built on for a good reason, that are now being developed. But unfortunately, the climate is also changing as well. So not only do we have changes on the exposure or the population side, we also have changes in hazard. And there's very good reason to believe that a warmer climate will indeed equal a wetter world. And in its most simple form, the reason for that looks like this. We've known the physics behind why a warmer atmosphere will lead to more extreme rainfall events for a few hundred years now, going all the way back to the 1850s. And the two gentlemen on your screen are Rudolf Clausius and Benoit Clapeyron. And they formulated something called the Clausius-Clapeyron law. And that defines how much water vapor can be held in air at different temperatures. And what we see is that the water carrying capacity of air, of the atmosphere, increases as the temperature increases. And that relationship is around a 7% increase per 1 degree of warming. Now, interestingly, we are seeing that level of, and even scaling above that, occurring in the observed record. So we are seeing, as the temperature increases, we're seeing localized rainfall increasing in the observed record. And in fact, we expect pluvial flooding, so flooding at local levels, so caused by intense localized rainfall. We expect that to amplify almost everywhere around the world. That's something that will amplify almost everywhere. And to compound future flood risk amplification, we also have rising sea levels as well. And rising sea levels are occurring, again, almost everywhere. It's only within polar regions that we don't see a rise in sea level down to melting ice caps. And one of the things I'm often keen to emphasize is that climate change doesn't represent an existential threat, I wouldn't say, for most people. It for sure represents some really significant problems for us to overcome. But it does represent an existential threat for some people, and that is down to rising sea levels. If you live in very low-lying coastal regions, if you live on very low-lying islands, for example, then these rising sea levels do indeed represent an existential threat to you. That they are that profound a risk moving forward. So hopefully that gives you some indication that flood risk is indeed a problem that we need to think about at some length. So what can we do about it? Well, we can actually build computer models that simulate flooding. And we can build these models to within, I would argue, some pretty incredible levels of accuracy. And if we can build models, then we can build models to identify risky areas. And we can even use these models, as they are physically based models, we can use these models to undertake projections moving forward and try to understand how risk might change in the future. But if we want these tools to be useful, then we need them to operate at scale. So it's great having models of single river reaches, but if you really want to have universal tools that can be used by everyone, like I go back to the point a few slides ago that flooding impacts 1/3 of the world's population. So we need comprehensive coverage. We need these models to operate at large scales. And we also need the ability to rerun these models as we get more observations in place. And also as we get things like new climate models in place. We need models that can simulate under different climate scenarios. So the requirement on us as modelers is to provide these tools. And we need models that can be built and executed quickly. We need frameworks that can simulate flooding for the whole planet. And we need to be able to rerun them very quickly when we get things like new observations in place and new models. So this brings us to the question of how we build these models. How do we build global scale models? And again, you could probably swap out the word global for the word automated. Well, actually, the basic theory behind the models that we build here at Fathom, and indeed anybody building dynamic flood models, the physics behind them is, again, really well understood. It goes, again, all the way back to the 1800s. We can solve formulations of the shallow water equations, but simulating models of flood risk does represent some quite unique problems. Because flooding is so spatially complex, it can change over very short distances. You can be wet in one location and dry a few meters away. Well, the models need to be very high resolution, and they need lots and lots of input data sets as well because of that locality. When you're running physics at high resolutions at global scales, well, it becomes very difficult to do that because of the computational demand of these models. So we need these things to be really efficient. If I could just spend a few moments breaking down the models themselves, and this, if any modelers listening in will be familiar with these different components of a flood model. And there are other things we could add in, like flood defenses, for example. Some of the basic building blocks required to build a flood model. The first one would be terrain. So we need to have representations of the Earth's surface. And if you're really lucky, you might have some really accurate and precise data in the form of something called LiDAR data, which is laser altimetry data. And this is on your screen this is a stretch of the River Severn. And you might also be lucky in having some input observations in the form of a gauge. And that gauge can be used to define the mass of water to plug into your model in time in the form of a hydrograph. And if you're really lucky, you might have time to go out and survey the size of the river channels. And if you plug those things together into a hydraulic engine, so something that solves formulations of the shallow water equations, well, then we can build computational models. And often this is how models are built. They're built by engineers around the world. And this is what I would call kind of gold standard models. The models that are built in this way can often be incredibly precise and incredibly accurate. And indeed, I've got an example here of a simulation of Carlisle in the north of England. And validation of these kind of local scale engineering type models show that they are often within error of observations. And what we mean by that is that there are errors associated with measuring flood extents and flood depths. And the models themselves get within that error. So the models are effectively as good as we can measure them to be. The models are frankly that good. But that was the state of the science going back 10 to 15 years ago. We were able to build these kinds of models. The real problem is, again, thinking about scale and how we go from local scale models where you have lots and lots of information and frankly, lots of time to go out and derive things like the size of river channels. How do we go from those kinds of models to models that cover the entire planet? Well, until quite recently, the problems precluding us from doing that were insurmountable. We just couldn't do it. And because of that, this is a kind of a picture of the world back in 2015, looking at the provision of national scale flood risk information. So if you lived in one of these countries, what kind of information could you get a hold of to define how exposed you might be to this peril? And actually, the majority of the planet had nothing in place. There was no comprehensive information available at all for the majority of the planet. And surprisingly, even in countries like the United States, only had partial coverage. And that's just down to the size of the United States. Building a patchwork of models across all of the United States, just incredibly difficult and frankly expensive to do. They've actually spent over $10 billion building those kinds of models. And still, you don't get comprehensive coverage. So how do we get comprehensive coverage? How do we build those kinds of models? Well, this is a list of problems that we wrote down as a team at the University of Bristol over 10 years ago now. And the list, as it stands, consists of terrain data. So we need ways to measure and observe the Earth's surface around the world. And believe it or not, we still don't really have what I would argue to be a gold standard terrain data set of the Earth's surface. We need to know where the rivers are and how big they are. We need to have ways of defining boundary conditions. We don't have gauges everywhere. In fact, we don't even have gauges on all the rivers in the UK or the US. So we need ways to estimate extreme boundary conditions for things like the coastal sea level, rivers, and even rainfall. We also don't have information on defenses. For the majority of the planet, actually, we do not have observations of where defenses are. So we need ways to try and estimate where they might be. And the last 2 points are perhaps a little bit boring, but maybe not to some in the audience. And that is around how we actually build these frameworks, because they need to be automated. You can't manually build these kinds of models and expect to get comprehensive coverage and have a model that can be rerun quickly. So there needs to be an element of automation in these models. And we also, again, need it to be efficient. So we're simulating somewhat complex physics at high resolutions at large scales. So the models need to be efficient. Now, I want to spend a few minutes just talking about some of the solutions that have been put in place to solve some of these problems in the past few years. Again, back to the beginning of the talk, if you do want to get more detail around how we actually solve some of these problems, then do visit our research timeline. There's also other webinars where we go into even more detail around the models themselves. So there's plenty of resources on our website for you to engage with. So firstly, terrain data. Well, this is the most critical component of any flood model, frankly. As complex as the other processes can be in these models, if you don't have a good terrain model, then your flood model will not be very good. Fundamentally, water flows downhill, and you need to know where downhill is in your flood model. Now, until relatively recently, we have really suffered, and by we, I mean the community of flood modelers building large-scale models, have really suffered from the availability of accurate terrain data sets around the world. And on your screen at the moment is an example of a global terrain data set on the left, and on the right is a local terrain data set, and that is a LiDAR data set, so something that's been collected locally using high precision, high accuracy laser equipment. What you can see is that on the left, the data set is subject to lots of noise and also lots of error. And the error in global terrain models, a lot of that comes from the fact that they are radar-based products, and radar, unfortunately, bounces off the top of trees and bounces off the top of buildings. So what you end up with in raw global terrain data sets is a surface model, not a terrain model. And by surface model, I mean you're mapping the tops of trees and you're mapping the tops of buildings. Now, if you're a flood modeler, you need those artifacts removed. So you have to remove those from the terrain data sets. And the community of flood modelers around the world, I would argue, has become the world-leading experts in cleaning up these kinds of terrain data sets, because we stand, frankly, to gain so much from having accurate terrain data sets. And we've been doing that for 2 decades. So back when NASA released the Shuttle Radar Topography mission, we began working with these global scale radar products. And we've now transferred all of those learnings onto the latest global radar-based satellite mission. And that's something called Fathom X. And Fathom X is a real significant step forward in our ability to map terrain around the world. We can actually also leverage new technologies like machine learning as well to clean up these data sets. So we're using machine learning to remove artifacts from a global surface model in the form of Fathom X. And the latest global terrain data set is something called FabDem Plus. And FabDem is Forest and Buildings Removed DEM. It's not only FabDem, we also stitch in LiDAR wherever it exists in the world. So it's actually FabDem or cleaned up Fathom X, only in the worst case scenarios. And I just wanted to show you on the next slide why these terrain data sets are important. And what you'll see on the left-hand side of your screen is our old global terrain model based on that shuttle mission that I spoke about. And in the middle, you'll see FabDem, and on the right is a LiDAR model. And the LiDAR model is effectively where we want to get to. And hopefully what you can see here is that we really are, I kind of crudely say, we're kind of halfway now between where we were and where we want to be with FabDem. FabDem is a real significant step forward in our ability to model flood around the world. On to discharge estimation. Now, I don't have much time today, so I've chosen to talk about boundary conditions in the form of river flooding, but we also, when building global models, have to think about how we define boundary conditions for coastal regions as well, so extreme sea levels, and also think about extreme rainfall in our flash flood models. But some of the parallels or some of the explanations here around how we derive these boundary conditions do translate to those other boundary conditions or perils as well. Now, when you're thinking about defining discharge or river flow in a flood model, There's a few ways that you can do that. And two of the most distinct ways you can do this are by building hydrological models. So you can build computer models that represent the hydrological cycle and use those models representing physical processes to define extreme flow behavior in rivers. And another thing you can do, and something that we have leaned towards and indeed deploy to define the extreme flows in our models for our hydraulic models, are statistical methods. Now, statistical methods in hydrology have typically focused on something called regionalized flood frequency analyses. And that's a long-winded way of saying that we link extreme flow to catchment characteristics. Now, this is another instance in which machine learning has really proven to be an incredibly valuable and useful tool for us as modelers, because we can use the idea of linking a bunch of catchment descriptors to an output is almost precisely what machine learning models are set up to do. You have predictive variables and target variables. And we've used machine learning to take a bunch of globally observable catchment characteristics and link that to flow behavior, and then use that model to define boundary conditions anywhere in the world. So once we've defined our boundary conditions and we have an estimate at least of how much water to plug into the models anywhere in the world, the next thing to think about is where we actually plug in that discharge. Where do we plug in that mass of water? Well, we need to plug these masses of water into rivers. Representing rivers in flood models is critically important. We need to know A, where the rivers are, and B, how big they are. But there are no observations of how big all the rivers are in the world. Indeed, until recently, we didn't even have information on where all the rivers in the world were. There were some significant errors even defining it, where the rivers are. And I've got an animation here to show you why the representation of rivers is important. Now, this is the Mississippi River, and this is near Memphis in Tennessee. And what you'll see here, hopefully, is that it almost looks like there's two boundary condition inputs, one at the top and one at the bottom of the domain. But in fact, there's only one inflow here, and that's at the top. But what is happening is that the water is being conveyed through the river channel. And as it reaches the bottom of the domain, the Mississippi begins to meander significantly. And those meanders introduce resistance in the model. And that resistance results in backwatering effects. That's compounded by the terrain itself constricting towards the bottom of the domain. If you don't represent river channels, then you don't represent these dynamics correctly. And frankly, your model will not be very accurate. So how do we define how big the rivers are? We're getting much better now at defining where they are, but how do we define how big they are? Well, we had something of an epiphany a few years ago, and that was to link the size of the channels to estimates of discharge. And in doing this, we can't measure the size of all the river channels in the world, but we can observe how frequently they fill up. And that's the assumption we use here, is that we link the size of the channels to estimates of discharge. And if you do this in a model, one of the ways you can do this is by back calculating, again, some old mathematics in the form of the Manning's equation. So you can rearrange the Manning's equation and plug in all of the variables that you can either observe or estimate, and use that to define a wetted perimeter. Now, this is something we did a few years ago, and we thought it was quite smart until we actually tried testing it. And a word of caution here, that deploying these assumptions in that way doesn't work very well. And the reason for that is that it does not account for backwatering effects at all. So the domain here shows you that I think this is Austin in Texas, and the rivers in this domain are designed to, or we assume, are conveying a certain frequency here. And this is a 1 in 2 year event. And what we see is actually water leaving the channels. And that's because we do not account for backwatering effects when you apply some simplistic assumptions like rearranging the Manning's equation. Instead, what we've now developed is the channel solver. And the channel solver is effectively a pre-simulation. So it's a pre-simulation that allows you to iteratively solve how big a channel needs to be to convey a certain volume of water. And that allows us to implement our assumptions in the way that we want them to be assumed. This is all open in peer-reviewed papers, so do visit the research timeline if you'd like to define or see how we actually do this. We also don't have observations of defenses everywhere, and there's a bunch of ways in which we can define defenses around the world. We've spent a lot of our time, particularly in the US, trying to define where defenses are. The options for doing this consist of representing defenses in the terrain model. So you can do things like try and preserve levee heights in your terrain model, or indeed alter your terrain model. We could represent them in the channels, so you could change the size of the river channels to convey certain volumes of water, depending on your defense assumptions. You could also reduce the amount of water being plugged in. And you can also do this as a post-processing step as well. So you could just run your simulation as an undefended simulation, and then post-event go in and crop out the areas of water in which you think defenses exist. Although that does introduce some problems around removing mass from the model. So you're not really moving that mass elsewhere in the domain if you're doing it as a post-process. Fathom's undertaken actually all of these methods. So we represent defenses in a bunch of different ways. And I will say that in terms of the products that we provide different formulations of our defense assumptions depending on the use case. So for an insurance company, for example, we might implement more assumptions around defenses, whereas for engineers, we will only plug in defenses that we know exist. My last 2 points on the modeling, very, very quickly. We need really efficient ways to solve these physics. I will simply say on this, there's numerous peer-reviewed publications defining how we can do this. Visit our research timeline. We now have formulations of the shallow water equations operating on orders of magnitude quicker than we did even a few years ago. And lastly, on the modeling itself, the framework and how we build these automated structures as opposed to building local models, how we actually deploy something that can be run for the whole planet, is again defined in some peer-reviewed papers. I'd probably point particularly to the paper in 2015, which is in small on the bottom left-hand side of your screen. In that paper, we define exactly how we stitch together these frameworks and deploy them in an automated way. The models themselves are run as a series of tiles around the planet, and those tiles are then stitched together as a post-processing step. But these frameworks do enable us to provide views everywhere for the whole planet. And I want to show you now some of the progress that's been made over the last few years, building these global scale models, starting with a really data poor area. And this is somewhere in Zimbabwe. And it's somewhere that was interesting for some clients of Fathom's because there's a hospital in the middle of your screen. Now, this is version 1 of our global model. And as you can see, we tend to capture some of the flooding on large channels quite well. This improved a lot with a new iteration of a global terrain data set in 2019. But this is now really converging on, I would say, local scale models with the introduction of the channel solver and primarily the introduction of FabDem+. We're able to represent flooding even on the smallest flow pathways. Do the models work? I've got some snippets of some validation metrics here. And I would argue that the models have skill, even at global scales. The models now have really usable skill. And the validation metrics do indeed demonstrate this. If you're validating a flood model, one of the ways that we do this is by comparing against gold standard local models. And that's what we have here with the FEMA data set. And what you can see on the right is the Fathom data overlain over what I would call a gold standard model. And in doing this pattern matching, where we're seeing how well our extensions match local models, for example, one of the metrics we use is something called a critical success index. And we're typically aiming for between 0.6 and 0.8 when you're thinking about flood models, just because of the uncertainties in the benchmark data themselves. And in the US, these are some validation metrics that are kind of being published at the moment for our US and global models. And what we can see is that even the global model has real skill in representing local scale models in the US. I've got another somewhat new piece of validation work to show you as well. And this is a simulation of the dam near Kherson that collapsed earlier this year. And as part of our work with the Foreign Office here in the UK, we were tasked with deploying our model framework really, really quickly. And the hatched areas that you can see appearing on your screen are satellite extents collected in time. Now, what we were able to do by running our model framework really quickly was to provide I would argue, a pretty accurate representation of what the extent would look like almost in real time. This model was deployed in a matter of hours, as opposed to waiting for satellites to overpass. So I'm gonna wrap up my part talking about some of the implications of these models and what they tell us about risk. And one of the hopefully obvious and indeed fundamental ways in which these models tell us something new about risk is just in terms of the number of people exposed to flooding around the world. When you have a comprehensive model, unsurprisingly, it gives you it gives you amplified numbers in terms of the number of people exposed to flooding. And on your screen, you can see here that the red data are FEMA flood maps in the US, built by local scale engineers at local scales. And as I mentioned on a slide a few slides ago, where the two models exist together, they give largely the same answers. So all the blue you can see on your screen here is just down to smaller flow pathways not being represented by the FEMA data set. And if you put some numbers to this in terms of exposure, what we see is that actually there's a threefold increase in the number of people exposed to flooding in the US. And again, this is just down to the models not being comprehensive from the government agencies. This is my last slide. I just wanted to say something about risk moving forward. And again, hopefully speak to why I think these global scale models are really useful. As part of some research we undertook last year, we looked at using our model in the US to explore exposure and risk in the United States to flooding now and in the future. And by looking at the future, we were looking at two variables. So we're looking at change in population and change in climate. What we found is that, yes, there's a significant increase in flood risk in the United States, according to our model. But perhaps surprisingly, the vast majority of that amplification in risk is down to population growth. It's down to people developing areas in which you shouldn't develop. And around 20% was due to climate change. Now, I think one of the take-home messages, hopefully amongst many in this talk, is that the majority of future risk is actually historical risk. And what we mean by that is that the risk that exists today in terms of that the hazard components of these models can already capture most of the risk moving forward. And as I've said, the model frameworks we're deploying now really do have skill. So I would argue that we already have the tools in place to avoid the majority of whatever future risk holds in store for us. With that, I'm going to hand over to Nat now to give you an introduction to global climate models. There will be a separate talk after this where Nat will go into some detail around how we actually plug these models in. But over to you, Nat.
Thanks, Andy, and thanks everyone for joining us. So yeah, as Andy said, I'm going to give a very brief overview of some of the challenges associated with representing the impacts of climate change in global flood models, and there will be another webinar that will discuss this in more detail. Next slide, please. So this is just a figure from the latest IPCC report, just to kind of give a little bit of context and motivation. Andy's already kind of referenced some of it. So on a regional level, as the climate warms in the future, we're expecting heavy precipitation events and pluvial or flash flooding to increase in most regions with high confidence. So this is kind of highlighted in the left most red box. You can kind of see that the dark purple area indicates an increase and that we have high confidence in those changes. The bars next to that shows river flood projections, and again you can see most regions are projected to see an increase in flooding, but with more uncertainty now. So there's a kind of a larger number of regions that have that sort of lighter pink colour, suggesting that there's kind of more model disagreement in that signal, but an increase is still expected. And then if we look at the right hand red box, then we can see that relative sea level and coastal flooding are projected to increase in most regions again, and also with high confidence again. So there's not much kind of uncertainty with coastal flooding. It's expected to generally increase with sea level rise as the climate warms. And there is significant variability on different spatial and temporal scales, and depending on the flood type, but these are the kind of main headlines for how we expect climate to change in the future. Next slide, please. So how do we model future changes in flooding on a global scale? So the main way to anticipate future changes in climate and therefore in flooding is to use models. And specifically, we use a chain of models for this application. Typically, we start with a climate model, as you might expect. So on the left-hand side, you can see we have general circulation models or regional climate models. So these are kind of computer simulations of the Earth's climate system, and they include a load of different components. So the atmosphere, the ocean, land processes, land surface processes, and ice sheets. They simulate the physics of the climate on a 3D grid. So that includes the flows of things like air and water and mass in the atmosphere and ocean and between the atmosphere and the ocean, as well as heat transfers. And from them, we can extract information about how climate variables that are relevant for flooding might change in response to climate change in the future. So things like extreme rainfall, how hurricanes or tropical cyclones, as they're known, might change, and how sea levels might change. And we can then link these GCMs, so the output from these GCMs, to different types of models, such as hydrological models or coastal flood models, which you can kind of see in the central panel, to estimate how flooding may change in the future. However, as you might expect, Andy's alluded to it already, most of these different models are, including the GCMs, are really complex, expensive to run, and they're not always right. So there are some challenges associated with using them. Next slide, please. So I'm just going to kind of very briefly touch on what some of the main challenges are associated with coupling these global climate models to global flood hazard data. So there are a number of uncertainties associated with the climate models themselves. One is known as model uncertainty. So if you have been to previous talks about climate models, you may well have seen this quote previously. It's quite a common one, but also quite a useful one. So all models are wrong, but some are useful. So we acknowledge that there are limitations to the models, there are uncertainties in them, but actually they can still give us really useful information. And that's kind of why we continue to kind of use them and develop them. And they're kind of the best tools that we have for looking at how future climate might change in the future. So all of these different general circulation models, global climate models that we use, are developed by different institutions around the world. They were developed over different periods of time, and they include different components of the Earth and climate system. They mathematically represent or parameterize different climate processes rather than physically representing them, and these parameterizations are often done in different ways. And because of that, all of these different models have different strengths and weaknesses and sensitivities. And actually two different models may give a different answer in terms of how the climate might change, even when run with the same forcing conditions. So even if you double CO2 in both of them, they might give you a completely different future climate signal. With precipitation, for example, even the sign of change can be different in some regions between different models. And so the way we reduce this uncertainty and try to understand it is to use ensembles of different GCMs rather than relying on a single model. And then you can assume that if you have multiple models that agree on the same signal of change, then you can have more confidence that that may be physically realistic. And the figure just shows the couple model intercomparison project kind of sixth phase, which is a huge global model intercomparison project across a whole range of different institutions to try and get a grasp on model uncertainty. Next slide, please. Second uncertainty we have about future climate is scenario uncertainty. So we don't know as a world and as a community what's going to happen in the future, what climate policies will be adopted and by which countries, how greenhouse gas emissions and land use and population will change. And it's therefore necessary to consider a range of different emissions scenarios which kind of sample different pathways that global socio-economic development might take. And an example of these shown in the plot are the shared socio-economic pathways from the latest sixth model intercomparison project. But there are also a range of different other scenarios out there, such as the more industry relevant NGFS scenarios. And on the plot, you can just kind of see you've got the very high emissions scenarios with high levels of CO2 being released represented by the red colours, and then the lower emission scenarios with CO2 removal from the atmosphere represented by the blue. But you can see that in terms of the amount of CO2 that is released under these scenarios, there's a huge amount of range and difference between the different assumptions made. Next slide, please. And this all means that when you follow that through, input it into the climate models and get your future climate projections, you get a whole range of different assumptions about how climate might change in the future. So again, you've got your kind of red high emissions scenarios where you see very high levels of global warming of, sort of 4 or more degrees C, and then your lower levels of warming for your lower emissions scenario represented by the blue colours. Next slide, please. The third uncertainty associated with climate models is known as internal variability or natural variability. And this is related to the chaotic nature of the kind of climate in Earth system. And it really confuses the kind of anthropogenic climate change signal, particularly over the next few decades. So if we look at the plot here, this is observed global surface air temperature. And you can see that there's a general increase in the mean temperature as you kind of move through time, but actually there's a significant amount of interannual variability superimposed on that, with kind of different years showing higher or lower temperatures around that kind of overall signal. Next slide, please. And you can characterize internal variability in climate models by using large ensembles of simulations run using the same model and the same forcing conditions. And then any differences between the different ensemble members are due to internal variability. And the plot here illustrates how internal variability accounts for a larger amount of the uncertainty in global mean annual precipitation for the present day. So that kind of orange color around 2020 is quite a significant amount of the uncertainty that we see. But actually, by the end of the century, most of the variability, most of the uncertainty is associated with model uncertainty or emissions uncertainty, and that internal variability has a much less of an impact. Next slide, please. So if we now assume that we have our climate model data, we now need to think about how we can link it to our flood model data. And as I mentioned, climate models are really highly complex, and that means that they use a huge amount of computing power on supercomputers and also time to run. And this means that they're generally run at relatively low spatial resolutions compared to the kinds of localized scales that we're interested in for flood modeling. So to get a better idea of the different scales that we're talking about, the grids here show topography at different spatial scales. So the top panel shows the kind of common resolutions that global climate models have at the minute, which is sort of 150 kilometers squared per grid box. And you can see that for the region we're looking at here, that only really includes a few grid boxes. Some of the higher resolutions models in CIWEM have a resolution of around 25 kilometers represented by the middle box. And you can see that there are many more grid boxes for this particular region in this figure. And you're starting to resolve some of the kind of more finer scale details. And then the hazard maps that we at Fathom provide are 30 meters, shown in the bottom level of panels. And at that scale, you can really start to see that you can resolve more of the local features like valleys and the kind of higher topography that are going to have an impact on floods and flood driving processes. And at resolutions of tens or hundreds of kilometers, which are the ones often in climate models, processes such as convection that produce flood driving rainfall are often missing and parameterized. And therefore, we need to downscale the GCM data to find the resolutions in order to be able to use it in our flood models. Next slide, please. So there are a range of different methods available to downscale climate model data. The most common is statistical downscaling, and this involves identifying statistical relationships between predictors of local climates and local climate variables. And the relationships are then applied to the GCM output to give us the kind of higher resolution data. So one example of this is the delta change or change factor approach that's been used by Fathom in our global flood maps product. If we look at the plot on the right-hand side, this kind of gives a very simplistic illustration of that. So to calculate our change factors, we basically take the ratio of changes in a variable like extreme precipitation between a control set of GCM simulations, so that will be for a historical period, and then a future GCM simulation of, for example, the end of the century. And then we take the ratio between these two periods, and that gives us our change factors, which we then apply to local observations. So if we, and the way we do it at Fathom is we normalize that by the change in global mean temperature. So if we look at the plot in this very simplified example, a global warming level of 2.5 degrees C is associated with a change factor of 1.5 or a 50% increase in extreme precipitation, for example, if that's what we're talking about. Another example is weather generators, which is a way of statistically and spatially downscaling data where you essentially take higher resolution observed precipitation and artificially create a stochastic precipitation time series at a kind of higher resolution spatially and temporally that replicates the behavior of the observations. And then you can update that for future climate by calculating change factors from regional climate models, which I'll discuss in a second, and then applying those to the relevant parameters in the weather generator to give you a long time series of kind of future climate data at higher resolutions. Next slide, please. And then a different approach to downscaling is to use regional climate models. So this is known as dynamical downscaling. And these are much higher resolution models that cover a smaller area. So this is illustrated in the plot on the right-hand side, which shows the Cordex project, which is kind of a whole selection of different regional climate model domains that cover the globe. And therefore, so with the output from general global climate models or observational data as boundary conditions. And then due to the smaller area being modelled in these models, they can be run at much higher resolution. So you start to get some of the kind of smaller scale processes, such as convection, being better represented. Next slide, please. Finally, there are some temporal limitations with climate data that can pose a challenge. So for flooding, we're interested in kind of the high impact, low frequency events, but just due to the very nature of these events, they're very rare. And that means that really like long time series of climate data or multiple ensemble members are needed to properly be able to characterize these events. But due to computational limitations, these large ensembles, which may provide many centuries of climate data, are generally only run for a relatively small number of global climate models, which have lower spatial resolutions because of those limitations we talked about earlier in terms of computational expense. And so on the one hand, you have a larger sample of lower probability events, but they're more uncertain, and that's at the expense of spatial resolution and having multiple views of climate change from a range of different models. So one approach for this is to downscale the lower GCM data using a weather generator approach, which I've just discussed. But you can also, this issue is particularly relevant for tropical cyclones, which are obviously very rare events, particularly landfalling tropical cyclones. And so the way to get around this problem of the observational data set being relatively short is to use synthetic tropical cyclone models. So they produce synthetic records of tens or hundreds of thousands of years of tropical cyclone data, and that allows you to kind of get into how tropical cyclones might change in the future in terms of those really kind of rare high impact events. So this was a very, very brief overview of some of the challenges associated with the modelling of global climate and flooding in the future. And I'll now hand over to Gavin to talk about how some of these global scale flood models can be used in practice.
Wonderful. Thanks, Nat, for that. And hopefully you've got a good understanding at a reasonably high level of the science and the technology that we use to build large-scale flood models. So what I'm going to be doing is really looking at how we can deploy those models in real-world environments. So if we go to the next slide, within the engineering and AEC built environment, these large-scale maps are really used and applied at the start and early stages of projects, where people need to pull in data and make very quick decisions around maybe funding options, maybe site selection, suitability of routes or applications. So the idea is that this large-scale data can really help drive those decisions, those early stage and important decisions in any project, to then focus on the areas that need much more detailed flood modelling, whether that's using HECRAS, TwoFlow, or Jacobs Flood Modeler. There's a range of tools out there that really obviously get into more detailed flood modelling, and we work with a whole range of different organisations that use that data. So this next slide will give you a flavour of how our large-scale maps are deployed, not just within the engineering market, but across a range of other markets that extract value from our data from these very large maps, scale maps. So drilling down into some specific applications on the engineering side, if we now go to the next slide, we can look at how this data can be used for particularly site selection, the application across linear assets, critical infrastructure, and of course tying that all into the analysis using climate dynamics and really getting a better understanding of the impact of climate change on specific assets. Next slide, please. So if we look at sites assessment and selection, so this is where perhaps assets need an initial screening or profiling to look at those more critical assets that might be susceptible to flooding today. But of course, those assets that might be impacted today might be different from the assets that are impacted in the future due to climate scenarios. So this data is really used to provide that very rapid screening to identify sites and provide a consistent view across portfolios of assets that then the asset owners and the managers can then look at investment and decisions around which assets to support to make more resilient and which assets are less critical and perhaps don't need that level of investment. So the next slide really shows you an example of where this type of large-scale data can really be of value. This is a client of ours that uses this type of data for site selection for solar farms across the US. They inherited a portfolio of existing solar farms and used this data to qualify the impact of flooding across each individual site. And you can see here that this particular site is impacted to a significant level by fluvial flooding. Normally these sites would be written off, but because they had the sufficient data, they were able to rearrange the solar array to make this a viable site. If we now look at more critical infrastructure and linear assets, this is where we have assets that may be distributed across a large network or across large areas, whether that's transportation infrastructure, energy infrastructure, or comms. This type of data has been really important in giving that high-level initial view of those particular wet spots. Rail and transportation networks have benefited from this data, both projects here in the UK, in Italy, and in Canada. So let's look at how our data, next slide please, can be applied not just off the shelf in some of the applications that I've talked about, but actually if we take the modelling framework that Andy alluded to earlier, how can we actually develop flood data sets that are bespoke and meaningful to a particular project? This is a great example that was worked with. We partnered with Arab and the World Bank in Dar es Salaam, where we're able to provide information on the impact of flooding today, but also in the future under specific climate scenarios. And then we were able to overlay that with urbanization projections and changes in land use. And from that, we were able to identify the areas that were going to be impacted to a greater extent due to those changing factors. To mitigate that impact, we were able to work with Arab, where they looked at implementing nature-based solutions. And by overlaying those solutions into our model, we were then able to identify the areas that would benefit from those typical nature-based solutions and be of value. So we could do very quickly through our automated modeling framework, what if scenarios under climate change, changes in urbanization, and mitigating that impact through nature-based solutions. So that was one project. Another project that has been very large for us, next slide please, is with the Texas Water Development Board. On the back of Hurricane Harvey in 2017, the state government in Texas realized that they were really ill-prepared for the impact of such significant catastrophic events. And so they decided to do something about it. And they tasked the Texas Water Development Board to really identify flooding areas across the whole state, so they could work and develop and provide information at a more localized level to regional flood planning groups. However, when they pulled this information together, they realized that a large proportion of the state was not mapped. So they had a real requirement to get a consistent view of flood risk across the state. Next slide, please. So that's where we were able to deploy our modeling framework. First of all, next slide, please. We produced a totally new digital elevation model from the LiDAR that the state provided. And on the back of that, we ran that through our modeling framework, and we're able to provide a whole series of outputs. Next slide, please. based on the LiDAR, but also a consistent statewide view of pluvial, fluvial, and coastal flooding for a different range of return periods. Next slide, please. And what that allowed us to do was really provide a very detailed view of flooding across the state. And you can see in this image here where the Fathom data really infilled a lot of the gaps across the whole state. That data was very well received by all the regional flood planning groups, where some of them had never had a consistent view of flooding across their region. This project has been very successful, and now we're into phase 2, looking at climate variability across the state and overlaying that with urbanisation projections and subsidence. Next slide, please. So that's a very quick look at some of the applications. What I'd like to do now is open up the floor to questions and hand over to Andy.
Thanks, Nat. Thanks, Gavin. We do have a few minutes left. I know we tried to cram a lot into that session, but there are a few questions coming through, so I will quickly get through them as best I can. So first of all, we have a question from Tahira. Do you use NASA's satellite data for terrain data? We don't. We did for many years. So I would actually argue that the entire formulation of our company was based on open NASA data when it was made available. And indeed, the first 2 versions of our global data were based on NASA terrain data sets. And we spent quite literally, not myself, but the research group spent 2 decades cleaning that data up. But we now use European data in the form of the cleaned up Fathom X data called FabDem. So it's not NASA based anymore. It's data from the European Space Agency. A question from Iria. How do you represent defense as a post-processing step? Well, the mechanics of it are very simple. So you're just going in and effectively removing water as a post-processing step. So you're just cropping the water out. In terms of how you actually define where to do that, so you could use known defenses. So you could run a simulation. You could take a known defended area at a certain frequency. So, for example, this area is defended to a 100-year event, and you can just remove that water. But you can also build models that effectively give you estimates for defense severity. So, or how well are certain areas protected in terms of frequency. And you can do that using things like socioeconomic indicators. So you can take known defenses in regions where you have known variables such as GDP, for example, and then you can use that target and predictive variable, again, philosophy, to estimate where defenses might exist around the world. There's pros and cons to defenses as a post-processing step. A con would be that you're not preserving the physics of the water. So if you're just removing the water as a post-processing step, then you're not retaining the physics of where that water might go. But I think a big positive, though, is that in doing it as a post-processing step is that you can explore things like uncertainty in the defenses themselves. So a post-processing step is not computationally expensive at all, whereas rerunning the hydraulics every time for a new estimate of defenses becomes very expensive. So there's some real benefit to doing it as a post-processing step. Perhaps time for one more question from Amelia. Do you use the same software for fluvial and coastal flooding types? At the heart of it, yes, we do. So the model is effectively solving the same physics for flash flooding, river flooding, and coastal flooding. The real difference in the modeling itself when it comes to fluvial and coastal is in the boundary conditions, is in terms of how we actually, frankly, plug in masses of water into the model. That's where the variation comes, but it's just a change in the boundary condition. All of the underlying procedures for defining terrain and river channel size and defenses, they remain the same regardless of the peril. So it is the same software. I think there might be some more questions, but we can follow up after the event. But the time is indeed up. So I will finish by saying thank you very much for joining us today. Do visit our website. There's plenty more content there for you, webinars, research papers. So please go to the website if you want to get more from us. And hopefully we will see you at the next event. Thank you very much.